electrons. So the closer you are to an octet, the stronger your ionization energy is. But as we move down the periodic table, now we have an issue where the electrons in that new shell are very far from the nucleus. So it's easy to take it away. Okay? So the electrons that are really far from the nucleus are easier to remove because they're so far. Questions? Yeah?
What happens if you remove an electron from a noble gas?
It acts like a halogen. And it's actually a very good point. I was trying to figure out how I can best talk about what happens. If you notice, this is interesting, fluorine has a higher ionization energy than argon and krypton and xenon. We can actually massage the chemicals a little bit where we can actually have fluorine kick out xenon. And it makes a very strange gas called sulfur hexafluoride. And when sulfur hexafluoride bonds, it's a gas, but it's like really, really heavy. If you take a balloon full of sulfur hexafluoride and you drop it, it'll land like a water balloon. Like bloop. So yeah, you can actually make the noble gases react, and they act like halogens at that point. Yeah?
Don't the halogens in group 1 act very aggressively to each other because they have the extra one and they want that?
The alkaline earths in group 1?
Halogens?
These are the halogens.
Yeah, don't they act like
Oh,
each other?
yes, the halogens and the alkaline earth metals, or the alkaline metals, react very violently because it's a match made in heaven. The halogens want an electron. The alkaline earth metals, or the alkaline metals, want to give up an electron. So yeah, it's a really great match. This is why we make a lot of sodium chloride. And there's a video on Friday you're going to watch about that. Little cartoon atoms talking, going to a disco. Yeah.
So as you move like down the periodic table, does is it easier to give up an electron too?
Yeah, it's easier to take them away because they're so much further from the nucleus. All right, 2 trends down, 2 to go. How are we doing? Moving on. This is my favorite. Now you might notice in this little diagram I found online that the p block only has 5. There's a reason for this. This is electronegativity. Electronegativity is how strongly an atom can bully electrons, or how strongly an atom fights to get that last Pokemon card. So, do the noble gases want another electron? No, they don't. So these are our nobles right here that are not shown because they have no electronegativity. They don't want another atom or another electron. They've got all they want. So electronegativity is an atom's ability to attract electrons. And it should make sense. The closer you are to an octet, the stronger your electronegativity. This is the most important trend for the next unit, which is bonding. We're going to talk about how electrons act when they are near each other. So the highest electronegativity is given a level of 4. Fluorine is 4. The lowest, 0.7 down for cesium. You put fluorine and cesium together, they're like, yes, a match made in heaven. I want an electron. I don't care about my last electron, and so on. So, as we get closer to an octet, our electronegativity goes up. We get stronger and stronger. The pull for completing that octet gets stronger when you are closer to your octet. Now, this has another property which in many textbooks is its own property, but it follows the exact same pattern, so I don't include it, and that's called electron affinity. Affinity is a really interesting word. Affinity, well, I'll give you an example. Homer Simpson has an affinity for donuts. Okay? You have an affinity for pizza. Okay? So affinity is a strong desire for something, but it doesn't have another word. It's really more than that. It goes the other way too. Okay? If we said Homer Simpson has an affinity for donuts, that would mean that donuts also like Homer Simpson. some people have a social affinity. You know who your friends are. They just always fit into groups. They like going to social situations, and people like to make their friends. If you have a social affinity, you like being in social situations, and people in social situations like having you there. Okay? So it goes both ways. You like something, and that something likes you too, likes you back. That's affinity. So atoms that have a strong electron affinity, they want electrons, but those electrons also want to be with them. That's electron affinity. Does that idea make sense? Okay. Again, I don't make it its own trend because it follows the exact same pattern as electronegativity. And again, as we go down the periodic table, the atoms get bigger and bigger and bigger, and the shells get further and further away from the nucleus. So their strength for getting one more electron is less and less because the protons are you ready for it? Shielded by the inner electrons. What this means is this. The electrons on the outer level are shielded from the protons. The protons are pulling in on the electrons, all of them, but they're pulling on the outer electrons less. That's called shielding. So the electronegativity goes down as we add more and more levels, which should make sense. Okay? Questions? 3 down, 1 to go. Ready? Ionic radii. If atomic radii is how big an atom is, what's ionic radii? How big the ions are. Okay. Getting back to our original topic. Opposites do what?
Attract.
Attract. And likes do what? Repel. What determines an atom's size is the protons pulling in on the electrons. And the electrons are repelling each other. So if you have an atom that is this size, and you add another electron, that electron's going to be like, hey man, I need my space. And those electrons are going to repel each other, and the protons are going to have to divide their strength amongst more electrons. Does that idea make sense? So what's going to happen to the atom when you add electrons? It's going to get bigger. It's going to, if you add just an electron, then the electrons will repel each other, and the protons have to divide their pulling strength amongst more electrons. So as you add an electron, we call that an negative ion or an anion, and anions are always larger than their neutral atoms. So when chlorine gains an electron, the chlorine anion is going to have to be bigger than the chlorine atom, because now we have more electrons that are repelling each other, and the pull of the protons is evenly divided amongst more, or not evenly divided, but is divided against more electrons. The cation is exactly the opposite. This is where we're finishing today, by the way. So the cation is exactly the opposite. Cations happen when electrons are removed. And when electrons are removed, there's less electron-electron repulsion, and the protons can divide their pull amongst fewer electrons, causing the atom to compress. So in summary, ionic radii. The protons in the middle of the nucleus are pulling on the electrons, keeping the electrons around the nucleus. But if we add one more electron, those electrons are going to repel each other, electron repulsion, and the pull of the protons is going to be diluted amongst more electrons. So an anion, again, there's going to be a temptation to say anion. It's an ion. You can think of it as a negative ion. An anion will always be larger than its neutral atom. On the other end, cations, don't say cations, I know there's going to be a temptation to say cations. They're cations. Cations are always smaller than their neutral atom, because when you take an electron away, bink, the resulting electrons have less repulsion for each other, and the protons are pulling on fewer electrons, allowing those electrons to be pulled in tighter. Does that make sense? And there's one more thing that makes cations really small. It's my favorite. Follow the little green dot. Lithium. Hey, lithium, how many electrons do you have in your outer shell? Lithium would respond with what? 1. If you take away that 1 electron, what happens to the shell? Poof, it goes away. So if you take away electrons from the S block elements, if you take away potassium's last electron, that 4th shell just disappears. If you take away sodium's last electron in the 3rd shell, that last shell just disappears. So in addition to less electron-electron repulsion and stronger electron-proton attraction, it's possible a whole shell just disappears. Questions? Okay, I think we're done. Yep, we'll talk about that next week. Yeah?
What about like lithium ion batteries?